Digital design using Verilog for absolute beginners. Lecture 4. Data flow modeling. Data flow modeling for simple circuits. The gate level modeling approach works fine because the number of gates is limited and the designer can instantiate and connect every gate individually. Also, the gate level modeling is very intuitive to a designer with a basic knowledge of digital logic design. But in complex designs where the number of gates is very large, it is not the case. Not easy. So, for efficient designing, the designers prefer a higher level of abstraction than gate level. An important point here is the designer is aware of how data flows between hardware components, registers, and how data is being processed in the design. This model is more convenient to the designers. Another reason for importance of data flow modeling is unprecedented growth in gate density on chip, which made the gate level modeling very complicated. Also, presently automated tools are readily available to create a gate level circuit from data flow design description easily. This process is called synthesis. This data flow model is also known as continuous assignment model. This type of modeling or style is more suitable for combinational logic circuits where clock is not involved as any control signal. As the output of a logic gate is continuously driving the input of another gate, it is popularly known as continuous assignment model. The assignment statement starts with the keyword assign. A continuous assignment is the most basic statement in data flow modeling, used to drive a value onto a net. This assignment replaces gates in the description of the circuit and describes the circuit at higher level of abstraction. The assignment statement starts with the keyword assign. For example, assign A is equals to B, then C, B, or C. Similarly, A is equals B and C. Here our assignment is continuously active. The assign keyword creates a static binding between RHS and LHS of the above expressions. So, we written simulation, the output is continuously active. Continuous assignments are always active. The assignment expression is evaluated as soon as one of the right-hand side operands changes. The operands on the right-hand side can be registers or net or functions calls. Registers or nets can be scalars or vectors. The left-hand side of an assignment must always be a scalar or vector net or a concatenation of scalar and vector nets. It cannot be a scalar or vector register. Here net and reg are kind of data types. In simple terminology, nets represent connection between components. Example, wire B. Nets must be continuously driven and are used model connections between continuous assignments and instantiations, whereas the reg or register retains the last value assigned to it until another assignment statement changes their value. It's often used to represent storage elements. Net and register data types can be declared as vectors or multiple bit width. For example, wire 3, 0, A. Wire 31, 0, B. Then reg 7, 0, C. And reg 31, 0, D. Example, half other, module half other, S, C, A, and B. Input A, B, declare input ports. Then output SC, declare out ports. Assign S is equals to A, saka B, and assign statement for X or. Assign C is equals A and B, assign statement for logical and AND module. So this is the diagram half other sum. So i-add siya. So S is equals to A plus B. Then carry C is equals to A and B. And here's another example, 2 multiplexer. The block diagram of MUX is shown below. So the diagram 2, 1 MUX multiplexer. They have A and B and S, select. Then Y is equals to A, I think is times segment S plus B S. Then the output of MUX is Y is equals to A segment S plus B S. Here S is the select line and AB are inputs. Here two logical and operations, one NOT operation and one OR operations are involved. Using the assign statements, the Verilog can be written. A Verilog code MUX module my MUX 2, 1, A, B, S, and Y. Then output Y, input A, B, and S. Then assign Y is equals to A and S, approximate, and B and S. Then AND module in the above code and denotes logical and denotes not denotes logical or operations. Verilog code MUX. All letter. The same code can also be written by another simple method shown below. Module my MUX 2, 1, A, B, S, and Y. Then output Y, then input A, B, and S, and assign Y is equals to S. Ang ipangita. Then B and A. AND module. Note, here is the conditional operator Y is equals to B when S is equals to 1 and else Y is equals to A. This is a ternary operator. Conditional operator blank is a conditional operator which is a very useful ternary operator. The conditional operator takes 3 operands. Usage is condition, expire, true, expire, false, expire. The condition expression, condition expire, is first evaluated. If the result is true, logical 1, then the true expire is evaluated. If the result is false, logical 0. Then, the false expression is evaluated. Example number 3, full adder. Full adder has 3 input bits and 2 output bits, sum and carry out as shown in the diagram below. In the diagram, A, B, and C in are inputs and sum, C out are outputs. So this is the diagram. We have A, B, and C in. Then sum S, A plus B plus C. Then C out is equals to A multiply B plus B multiply CIN plus C multiply A. Then Verilog code full adder. Module M my FA1 S C out A B and CN and port declaration. Output S C out input A B and CN assign is equals to A taas B taas C, then X or operation. Assign C out is equals to A and B and C, and C is and A and module. For other 16-bit module my HA 16 S C out A B C CN output 15 0 S, then output C out, then input 15 0 A, and here A, B, and S are defined as wire. Input 15 0 B, and input C in assign S 15 0 is equals to A 15 0 times B I square of B, then 15 0 square of C, then assign C out is equals to A 15 0 and B 15 0 and B 15 0 and C and A 15 0. Then end module. 2 or 4 decoder with enable. Decoder is a combinational circuit that has n input lines and maximum of 2 square n output lines. The diagram shows a 2-4 decoder with 2 inputs A and B, enable pin E, and 4 outputs D3, D2, D1, D0. So we have diagram the decoder with enable 2 multiply 4 decoder. So we have A and B and E. Then DO, D1, D2, D3. Then the working of the decoder can be understood from the truth table shown below. We have inputs and outputs. Then encoder, we have 0, X, D3, D2, D1, D0. So 1, 1, 1, 1. Then 0, 0, 1, 1. Then 0, 1, 0, 1. Then D3, 0, 0, 0, 0, 1. Then D2, 0, 0, 0, 1, 0. Then D1, 0, 0, 1, 0, 0. Then D0, 0, 1, 0, 0, 0. Example number 2 to 4-line decoder. Module decoder 2, 4, A, B, E, and D. Input A, B, and E. Output 3, 0, D. Then assign D 3. So A and B and E. Then assign D 2 equals A and B and E. Assign D1 is equals to A and B and E. Assign D0 is equals to A and B and E. And module. Example, half subtractor. The diagram below shows the half subtractor. It has two inputs, A and B, and two outputs, difference D and borrow B. Difference is given by D is equals to segment A multiplied B plus multiplied segment B is equals to A square B. Then borrow is given by B B0 segment AB. Then we have diagram. We have inputs A and B. The code B. Then difference borrow D is equals to segment A multiply B plus A multiply segment B. So we have difference. Then segment A, B is borrow. Verilog code module half sub D, B, O, A, and B. Input A, input B, and output D, B, O. Then assign D is equals to A, B. Assign borrow is equals to A and B. And module. Full subtractor, similar to full adder, full subtractor has 3 input bits and 2 output bits, difference and borrow. The logic diagram is shown below. So we have A, B, C. Padulong siya ani sa kuan D sa tawag nga D, then X, B, paingon siya sa D code, D, C, magyapon, B, O, then N, Y, and 1, so B, O. In the diagram, A, B, and C are inputs and D and B, O are outputs. The difference of the full subtractors is given by D is equals to A square of B square B and C. B, O is equals to B and C. And A and B square C. So we have diagram full subtractor A, B, C, D, B, O. Verilog code module full subtractor D, B, O, A, B, and C. Input A, B, C. Output D, B, O. Then assign X is equals to B square C. Then assign D is equals to A square X. Assign N is equals to C, and assign Y is equals to B and N. Assign N1 is equals to X. Assign Z is equals to A, N, and 1. Assign BO is equals to Y and Z. N module. Verilog code another way. From block diagram, the assignment model is module full subtractor D, P, O, A, B, and C. Input A, B, and C. Output D, B, O. Assign D is equals to A, then B, C. Assign B, O is equals to B and C, and A and B. I multiplied B, C, then N module. So that will be all. Thank you for watching patiently. Thank you.